start with the second part of morning section. The first talk is will be given by Dr. Omar Tibolla, and you can see the title. Please, you have.
So today we'll speak about I will switch to a bit more particle physicist oriented talk. Speak about the cosmic ray origin, that is one of the longest question that is still unanswered in astronomy. This is part of quite big project, and it's a big project. So let's start with a bit of advertisement. Since 3 years we are gathering in this small town in the Italian Dolomites. By the way, is the town where I come from originally. We could gather the very, very best expert about cosmic ray origin. And I will give you a lot of links and a lot of paper reference during my talk. I will try to go very quick, but for the people that want to deepen, I will leave a lot of things. Here is the book, monograph book of the conference. It's open source. Given the success of the first, that we did the second, and the book is just in press. And you will have also some hard copies here in Belgrade, because there was 4 people from Belgrade attending the conference at this time. So this is the outline of what I would like to speak today. I will introduce what cosmic rays are and what we call standard picture of it, or better, standard law. We are very short about detection techniques, because particle physicists are a bit more used to this kind of techniques. Probably in astronomy, many people are not so yet familiar with that. Very quickly, I will go to unidentified sources and what they are, and go small zone. And I would like to spend a bit more time on this part, so on this particular source and what is this on and not. This source would have been very good. I saw that after this session there will be a session more dedicated to the galactic center. This is a source in the galactic center, but I wouldn't not have at all time to speak about this. So I move it to the backup slides. I have more than 100 backup slides, so if the chair will allow, we can go on to speak about this until the social dinner, even later. And after conclusion. So, what to say to cosmic rays? We have a natural accelerator that accelerates particles to energy that would not be ever possible to accelerate with artificial accelerators. And this is the spectrum you have been seen 2 million of times in your studies, in your career, and you see here, I mean, these are the most powerful accelerator, but the natural accelerator accelerates for several decades more. Actually, the other side of the medal is that with the LHC, you change the voltage, you change the energy of the particle you study. You cannot change the voltage of a supernova remnant or AGNs, so we are studying how this accelerator works in order to be able to use them indeed accelerators, particle accelerators. So this is what is called this is particle accelerator that have been called cosmic rays. They've been discovered more than 1 century ago by the Jesuit physicist from Germany, Theodor Wolff, by the Italian physicist Domenico Pacini, and after by the Austrian physicist Victor S., who got a Nobel Prize 20 years after for the discovery. But the discovery was quite mature. There was several other scientists working deeply on this subject. I mentioned here Colosser that would make a balloon flight much higher than Hess, with much more detailed results. And even fathers of the physics like Millikan, the one who discovered electrons, spent almost 20 years of his career working on cosmic rays. Actually, he worked 20 years to demonstrate that cosmic rays do not exist. But ironically, the term cosmic rays was used by Millikan indeed. After 20 years, he has to give up and admit that they exist. So we know them since more than 1 century, but we still ignore their origin. We don't know where they come from. So, and now I will go very quickly to say to you a bit of nomenclature in order to not be misunderstood in the next slides. Here the spectrum, here you see that we have several direct experiments with direct the cosmic rays. and several indirect approaches, so gamma ray telescopes and neutrino telescopes. Today, when I will speak about high energy, I will speak about energy above 1 GeV. When I will speak about very high energy, I will speak about energy above keV. So, the strange shape of the spectrum, since the beginning, was giving some hints, some ideas, some very rough ideas about the origin. So, as you probably remember, the spectrum is a power law, pure power law, with a slope 2.7 until the knee, so at around 10 to the 15 electron volt. After it gets steepened to, with a slope of 3, and until the ankle, and after it goes back to 2.7 until the GZ cutoff. So the energy where the you do not expect, cannot even understand how this particle can be accelerated above. This is called knee and ankle because they simply follow the shape of the leg. This slope was suggesting since the beginning that until the knee, this cosmic ray could have a galactic origin, simply because at 10 to the 15 the magnetic field of the galaxy would not be enough anymore to confine the protons, so the particles in our galaxy. Something unusual above, and above the ankle, people was thinking to have it extragalactic. Actually, that the higher part of the spectrum is extragalactic has been, I would say, almost proved recently, weeks ago, by the experiment. But all this rough picture actually is no more. I mean, actually we don't know anything about the origin at the current stage. I was speaking about direct and indirect measurements. The direct measurements, so measuring the cosmic ray itself, when I speak about cosmic rays, I speak mainly about protons. So they constitute more than 90% of the cosmic rays, as some advantage. But we want to know the origin, where they come from. And for this, the direct measurements are not helping so much, because the magnetic field, galactic and extragalactic, are deflecting totally the charged particle. So if a proton is accelerated there, in few parsecs I can see it coming from there to the Earth. So for this reason, our kind of study, the indirect approaches that have for sure the disadvantage to be an indirect approach are more useful, because if I see a gamma ray or a neutrino coming from there, I know that this implies that acceleration, a particle physics effect was happening in that region. This indicator effect I saw is gamma rays and neutrinos. Neutrino would be very useful, but I'm convinced that neutrino astronomy would be the future of the field. But sadly, I'm convinced that this will be the very, very, very far future of the field. So, what we mean by standard picture? Standard picture basically was described in the wonderful book of Going to the Silvestri in '64. What we take care today is only this short line. So, to explain the local density of cosmic ray, so roughly 1 electron volt per centimeter cube, you need that cosmic ray accelerated in supernovae remnant, considering a 30-50 supernovae rate. But not only, you need that at least 10% of the kinetic energy of the supernova explosion would be dissipated in accelerated cosmic rays. This was in astonishing good agreement with the typical amount of energy predicted in the acceleration of relativistic particles. I mean, probably you heard these names many times in your career: Joule, Fogg, Biermann. And from the observational point of view, this talk today will be mainly observational, part of the conclusion, was finding a very big proof in the last decades. In fact, in the observation at TV gamma rays was showing excess of gamma rays coming from the same region where we already know that there was some X-ray accelerated there from the previous generation of X-ray telescopes like ATCA, Rosat, and so on. This was considered a proof of it, but unfortunately, this was not so. I mean, the TV gamma ray signal in this kind of object can explain in two ways. The first is what we will call today the photonic models. So inverse Compton scattering of on background photons. And the other one is what we are interested in, because as I mentioned, 90% of the protons, of the cosmic ray is protons. We already know since decades where the electrons are accelerated. What we miss is only 90% of the cosmic rays. So this is the part we are interested in more. You see that the spectral feature predicted and measured at TV is basically indistinguishable. From TV only observation, you cannot distinguish at all between electronic models and hadronic models. But if you see close by, the two slopes are quite different. Let's put a bit more in evidence. For hadronic models, you have headaches. That more or less zero order approximation, you have a pure power law extrapolation from TV energy to lower energies, and something like a factor 3 less flux you expect from electronic models. For this, we build a satellite that is called Fermi-LAT to try to see if we could reply this question. We did. This is for sure, you have to ignore these slides. It's only a reference if you are interested in these particular sources. Today we will speak about Tycho, Cassiopeia A, 1713, and other couple of sources. So the first big news from Fermi-LAT is that the standard model works. We detected the supernovae remnant Tycho, and the electronic models of Tycho goes home. They are basically disproved. The hadronic model works, and the efficiency of the acceleration of cosmic rays is even more than 10%. So everything worked. I think that we could go home. I can go home, Diane can go home, Marco can go home. We go back to our towns to make agriculture. And even more, we also, I mean, this is more appreciated by the particle physicists. For two sources, that the IC443 and W44. Fortunately, yesterday there was very nice talk speaking about this guy, so this allowed me to go very quickly on these slides. We also detected the pi0 band, the pi0 shoulder better of this source. So we also, from a particle point of view, we are sure that their pi0 are created by proton-proton elastic interactions. And they give rise to this kind of strange shape of in the gamma ray spectrum. According to me, this is very nice measurement from a particle point of view. From our problem, so the origin of cosmic rays, for me this is not relevant at all, because these two guys are not supernovae remnants, so what we need in our ingredient at the beginning, but are supernovae remnants interacting with molecular clouds. In these two guys, the rim, the shock, if you prefer, of the remnant is entering a cloud of molecular material. So it's quite obvious that it's accelerating hadronic material, no? Ions and protons. But everything, I told you that everything could solve. The problem is that the standard model works for Tycho, but it works only for Tycho. The very best studied supernovae remnant from a theoretical point of view, and absolutely the most promising target for all the experts of the field, that is LXJ1713, show us a purely electronic spectrum. On the left you see painted a lot of hadronic models, and you see that in the best case we are 1-2 sigmas, 1-2 standard deviation outside the measurement for Fermi-LAT, while the electronic models go exactly straightforward into the observation points. So the very best case show us everything totally different. For all the other supernovae remnant I was mentioning in this green slide, the hadronic models are favored, but the leptonic models are not discarded in any of them, but of Tycho. But according to my vision of the problem, this is not the most crucial problem. Let's take another example, that is Cassiopeia A, and take the gamma ray spectrum taking an over hypothesis that what we see in gamma rays is coming only from hadronic interactions. We make simple general physics 1 integral of the energy, and we find that this is 2% of the kinetic energy of the supernova explosion at the beginning. So 20% of what we need to say that the standard model would work for this case. And please note that the Cassiopeia A is not a random explosion. This is one of the two most powerful explosions in our side of the galaxy. So the question is still open, and according to me is more open than ever. So what to do? Or you modify the standard model, standard models. Then I put standard models this in order to provoke all the audience, and not only 2-3 people of the audience. And for instance, there's a wonderful model by Jacob that show Cassiopeia A like a particle accumulator that was much more efficient in the past and much less efficient now. Or some funny ideas that I added because yesterday we spoke about Tony Bell. I was discussing this solution with Tony Bell, and I find it very interesting, even if I do not have any idea how to attack the problem. We are in a local bubble. We are in a bubble superimposed of 4 or 5 supernovae remnant explosions. And I was thinking that this would mean that our 1 electron volt per centimeter cube density is a lower approximation of what would be in the galaxy. But Tony, that is much more expert than me, consider this the contrary. Say that in this kind of solution you have more cosmic rays. So if this would be true, even much less efficiency in the supernovae remnant would allow us to prove the standard model. But we will not speak about this today. We will speak about alternative sources. That is, I mean, the other solution is to find other sources, but of supernovae remnant, that can accelerate protons to those energies. And I think one should do both, but today we will speak about pulsar nebulae only. If you look the TV gamma ray sky, you realize that you are not at all dominated by supernovae remnant. 7, 8 supernovae remnants are detected at this energy. The most dominant, by the way, dominant population is pulsar nebulae. So, how can this help? Because pulsar nebulae for construction is meant to be a leptonic accelerator. Well, there are several theoreticians that was making some very nice model with the idea that at the termination shock of the pulsar wind, one could accelerate protons along the electrons as well. If this is true, since these guys are much more, and as I will show you today, they live much longer than supernovae remnants, could help. But let's open another parenthesis. This is the last one for today, and after all the talks will be devoted to close this parenthesis, or try to do so. The absolutely most numerous population of TV sources is unidentified sources. So we see them, they are bright in TV gamma rays, but we don't know what they are, simply. If you go to the GV energy, so to the satellite energy, this can be even more dramatic. 67% of Eagle satellite sources were unidentified, and the galactic sources, so the galactic plane belt of Fermi-Lat, you have 62% of the source unidentified. So this is not only a problem of TV astronomy, but of GV astronomy as well. So I hope that I will convince you for the end of the day that all these guys are only pulsar nebulae. So if you understand the most numerous population of TV objects, and this theoretical step, that is the biggest step that we are having today, is correct, understanding unidentified sources could indeed give us some ideas, at least, for the full picture of cosmic ray origin. Let's give a very short description of detection technique for the reason mentioned at the beginning. As you know, but of far radio and the small window in invisible, everything is shielded by the atmosphere. Fortunately, we are here speaking, would be quite difficult otherwise. So for studying gamma rays, either you go outside the atmosphere with satellites, or you use the atmosphere as a detector, and you use Cherenkov detector. Let's start with the first one, that is, I was mentioning before, Fermi-Lat. Fermi-Lat is simply a Fourier conversion telescope. A gamma ray enter in an anti-incoincident shield that, in the case of glass lat, is a Bricon plastic scintillator Bricon 4508. This is absolutely the most important part, because the protons, that is what we are aiming to understand where they come from, actually are our background. Okay? For every gamma rays we have 10,000, 100,000 protons. So we have to get rid from the background in order to distinguish our signal. So let's imagine we do it, and Bicron give us an efficiency of 99.994. So at least we arrive to 1 photon to 1 sigma, more or less, ratio. And interacting in upper conversion foils, simply tungsten foils interlaid with silicon stripes for detecting the shower, and you create an electron-positron couple. On the bottom you put a calorimeter. In the case of glass, it's cesium iodide, where you try to absorb all the energy of the particle to try to get the energy of the incoming gamma rays. This is how it looks like. The only thing I would like to add is that Egret, that was 20 years ago, 30 now, meant to be the gamma ray satellite, was a per conventional telescope embedded in a gas chamber, because this was the particle technique at that time. And actually this was causing Egret to be basically blind above 1 GeV where it was built. Basically because the particle was coming in the calorimeter, was reacting here, backsplashing back to the anti-condition shield and being vetoed. So 50% of the physics of Egret, and in particular the most interesting part for the one who built it, was completely useless, was lost. The anti-condition shield for latte is tiled. We don't need the gas chamber anymore. Okay, I mean, it would not have been possible for Egret doing otherwise. I mean, if you put a tiled anti-condition shield, the gas would escape after a few minutes after the launch. So you basically you are putting a dead instrument in the space. Fortunately, the particle physicist was doing a better detector. And now it's tiled. So there are several tiles. If the incoming particle is here and you see this tile, for instance, in the bottom here there are more tiles, it's called ribbon, you can veto the veto. Okay, so the veto will tell you, oh, the anti-condition field is shining, there is a charged particles. The anti-veto will say, no, but it's here, not in where the particle comes, and you don't throw away the good data. So we have such a satellite. Why to go for Cherenkov telescope? Actually, we should remember, we should keep in mind that everything, if we are lucky, goes down with a very steep power law following the cosmic ray spectrum. We cannot put 100 square meter satellites in the sky. Oh, we could, but it would be slightly expensive. And so we need to have statistics and having very large geometrical areas covering the sky. This is why we need to do it on the ground, basically. And the other things I just mentioned, the Cherenkov telescope cost a factor of 10, factor of 100 more, less than the satellite. So basically, if you wanted to have a full picture, you say that the satellites that are here and the Cherenkov telescope that are here are complementary in terms of energy, in terms of integral flux, etc., etc., etc. How does it work? A gamma ray enters the atmosphere. The arithmetic shower is formed, the electron depositrons in the atmosphere go quicker than the light. When this happens, that the particle will than the light in the medium, in the air, they make Cherenkov flashes. You put on the bottom a set of telescopes, you detect and you measure your shower, and from your shower you get back you reconstruct the incoming gamma rays. This is the so-called stereo approach used by Hess by Veritas. And in addition to the very easy reconstruction, is one-to-one, as you can see here, there is another important point of this approach, that is the background rejection. And sea level, the most nasty background we have in the atmosphere is muons. As you probably remember from Kamiokan, the image and so on, the muons flash, Cherenkov flash appears like a ring. No? This is very true if the muons is flashing here. But if the muons is flashing very close to that telescope, your ring would not be distinguishable in experimental terms from the ellipse that you want to have. So you simply add a multiplicity in your system, you add a second telescope, and you impose your system that the signal, the event has to be seen at least by 2 telescopes. In this simple way, you get 100% rid of the most nasty background. I mentioned that this is one approach. The second approach was used by Magic telescope, is to use a much bigger collecting area in order to detect the much fainter shower and go much lower in your energy spectrum. The 2 approaches have both advantages. So Magic added a second identical telescope, adding the multiplicity to the system, and Hess was putting an enormous instrument in the middle, 30-meter telescope in the middle of the array. And for this, I mean, the step for all the collaboration, 5 minutes left, really? Ooh, so I have to go over quickly, is to build an enormous telescope of medium, small, and big size telescope in the middle. Another approach is the water Cherenkov. You can put this big tank of water to detect your particle shower. The extra advantage, one is a full sky instrument, and the other one is that it's not limited to the cycle. So we can observe during rain, snow, day, night without any problem. So let's go over quickly, because we are, in my plan I'm not even in the half of my talk. Sorry for it. So before 2006, the Hess survey paper, we knew only a few handful, 5, 6 TV sources, and with this paper we knew more than 20. The surprise was that the sources was not appearing where we know to be supernova remnant, pulsar nebula, etc., but 50% of the sources are unidentified. Now we know almost 200 sources, of which 120 are galactic, but this ratio, and this number is increased, is destined to increase very much. This is only the first year of Hawk data, so this, but this ratio, 50%, seems to resist. Here, every ball you see in this cartoon corresponds to one of the sources that we know. The red are the AGNs, the blue are the pulsar nebula, the yellow are the binaries, etc. And we are dominated by the gray balls that are unidentified sources. Now, I will go very quickly on this part because this is only the zoo of how these sources appear to us. So on the left panel we will see the TV camera sky, and on the right panel we will see the radio sky given by Molongo survey, or overimposed by green contours given by the X-ray satellite Rosatol's ROSAT, so the ROSAT All Sky survey. As you see, this first sky we have a quite bright TV sources and absolutely nothing in the lower energy. Lower energy, this basically means synchrotron, if radio and X-rays. This other guy has some X-ray counterpart, but unidentified, so it's a doubly unidentified source. This was representing a clear case when we discovered it of pulsar intermediate age pulsar nebula, because at the bottom of this comet-shaped tail we have a very powerful spin-down luminosity pulsar. We did a deeper X-ray observation, and the only idea we had goes home. So this is fully identified. Another source with no lower counterpart, this by our Japanese friend, are called dark sources. This was a source that was, after when we did the deep multivariate campaign, we discovered to be a supernova remnant. So this is the first supernova remnant discovered by, triggered by TV observation. This is a mess. This is a 1 degree source, so twice the diameter of the moon, where we have 2 supernova remnants, 3 high-speed down luminosity pulsar, one, actually 2 because my student discovered another one here, X-ray binary, etc., etc. So a mess. We have this kind of cases where in the same field of view we have 2 unidentified sources. This seems to be leptonic, this seems to be hadronic, but both are unidentified. There are also very exotic cases. I mean, this guy was discovered as a single source in the survey. Now we know that it is actually 3 sources. This is a supernova remnant interacting with molecular cloud. This is a pulsar nebula. This is fully unidentified. Or even exotic material. This guy appeared to be specially considered with a forbidden velocity wing. So a part of our galaxy where there are radio filaments that move at velocity that are not allowed by the rotation of the galaxy. This is a mass square. It's like 1841. But all the possible counterparts are very, very exotic. This is the other case that the TV astronomers likes very much, so the star forming region, and okay. Actually, what I show you in the zoo, I was completely cheating on you. I do not believe any single word I told you so far in this zoo. All these guys, for me, are pulsar nebula. So, let's take this case. That is a particular unique case that open new windows, according to me. This was discovered, it's quite bright, it's 80% of the crab, was discovered by me a long time ago with the crab, with the Hess array. The unicity of this source is that it is 3.5 degrees outside of the plane. So in X-rays, basically, you have one order of magnitude less absorption. So when I discover it, I say, okay, 1 week of work, I go to look the X-ray and radio archive, and we prepare the paper. The problem is that there was no X-ray counterpart. With this number x1, x2, x3, there are 3 Rosat sources. Rosat was not so precise, so these 4 Rosat are point-like sources that appear close by to the region. Okay, if this guy would be a pulsar, probably this guy is a pulsar with nebula. We have to discover why we don't see the nebula in X-rays, but this is the only hypothesis we have at this point. The spectrum does not help. You see the error bar in gamma rays does not allow you minimally to distinguish between hadronic and leptonic model like I mentioned at the beginning. So let's see, let's go to search for the counterpart. In infrared and radio, this guy doesn't appear to have a counterpart. SGPS in radio and Spitzer do not cover this region. MS6, that is less sensitive but is the same energy band of Spitzer, does not see anything. Anything means blank sky. And Modonclo see it but without evidence a counterpart. It's curious that this source that now is the diameter is more almost Gaussian, like all the sources in TV gamma rays, and is this red circle there lies on this very, very long 10-15 degrees radio rim. It's obvious that I don't have and nobody have any explanation how this rim, if it's a supernova remnant like Danka et al. Are thinking of, would give rise to a such compact TV emission. We have to look at CO molecular clouds. We look in them, the sources appear here, and it goes very close by to this very big molecular cloud, but again, it's 1 degree far away from the most dense core of the cloud, and is much bigger, so no possibility of counterpart. I already told you about Rosat. I got twice 600 Newton observation, I got once Chandra, and I got twice Suzaku campaign. Here you can see the data if you want. And now let's see what we see. Let's take the example of Chandra because it's the most clean data set we have only for this. All the sources are or purely thermal, but anyway they do not help us to establish the origin to identify the source. Let's take X1, the lost source, to see if this is a good counterpart. This is the only hypothesis of work we have so far. And we can start thinking that there is another hypothesis of work, because there is a very faint and extended X-ray sources. It's not visible in this plot, but the magenta circle is evidencing this. The problem is that this source here seems to be extended. If it is extended, our only hypothesis of work is going home. Because if it's extended, it will be or a supernova remnant or a pulsar with nebula, but it has nothing to do with our sources. Because as you remember, it's outside the trigonometric contour of our sources. No? So, if it is extended, our only working plan is going home. It is extended. Okay? So, it's not a pulsar. Even if it's a pulsar with nebula, we don't care, because there is no way that I can avoid to have TV emission from this pulsar with nebula, since it's so efficient and bright in X-rays. And so let's try to see what it is. Let's make the model. In X-ray you have the advantage that the spectrum gives you some information. Let's put a power low, so let's see if it's a pulsar with nebula. It fits very well. Let's take a thermal plasma, and it fits as well. So let's look in radio. In radio, this guy has the counterpart. By the way, you see every time that X1 is a bit detached from the X-ray and radio source. This was well described by Harris et al. In 1 decade ago. Rosat was having some problem in pointing, was flickering. Okay, so when I show the sources, I put only the statistical errors, but this is well the error of the machine, so the instrumental error of this. So we see it in radius. What it is, a pulsar with nebula or supernovae remnant, but what we are sure is that has nothing to do with the TV source that we are analyzing. So what it is? The absence of lower counterpart, low energy counterpart, especially in X-rays, would suggest that this is a purely hadronic accelerator. So something that accelerates protons without accelerating electrons and positrons. But this scenario is extremely disfavored. We are every time outside of the plane. At this galactic latitude, I want to see the counterpart. Okay? Because for having a hadronic scenario, you need target material, density of the interstellar matter. And this implies that you are at least maximum 1 kiloparsec far away from us. So this latitude, this distance, I want to see the molecular cloud, supernova remnant of whatever is accelerating only protons. On the other side, being outside the plane, if it's really outside the plane, would suggest the hadronic scenario because you would not have any target material. And this, in the next slide, I will show you that this is the only thing that works. Okay? And there is a backside that this would imply, for instance, let's compare simply with Geminga, so the oldest pulsar nebula in our neighbor, that this guy is very far away from us. I was considered heretic when I put 6 kiloparsec. Now a friend of mine have an idea that this guy is 40 kiloparsec far away. So we are looking in the direction of the galactic plane, 40 kiloparsec, on the other side of the galaxy, attached to the galactic halo. The next astronomical question is what and how can be a pulsar with nebula be there in the middle of nowhere? So, but there are a lot of hypotheses, hypersynectic stars and this kind of thing that probably during the question I will have time to discuss before the chair is, I still have 2 minutes. So, I was telling that pulsar with nebula could answer. In fact, this is the discovery of 1507 obliges us to think about new scenarios. Indeed, you have the magnetic fields goes down with the time as a power law. So roughly in 1000 years, the electrons, if electrons accelerated there, are not visible anymore for the current generation of X-rays. While the TV gamma rays go on cluster. The electrons that make encephalic Compton go on for 1 million years to cluster. This is what we see, for instance, in 1825. That is one of the prototype of pulsar with nebula studies in the last decades. So let's see an example of the Jager, a cartoon, a movie, to see how it appeared. So basically you have the X-rays that go down very quickly because it depends one-to-one to the magnetic field, and the inverse Compton that order is 0, order 1 doesn't care about the magnetic field, that continue clustering. So let's take this pulsar with nebula 21.5 and let's go on with the time. This is 100 years after the explosion of pulsar formation, 300, 600, 1000, 1600, 3000, 10,000, 25,000. You see that after 25 kilo years, you have a very bright inverse TV gamma ray source, while you don't see anymore anything in X-rays. Okay? So let's apply this cartoon to 1507. 25 kilo years does not work, but 50 kilo years would work. This was a cartoon done by Oki Jager, probably the best leptonic astrophysicist of the universe, and a great man in addition to great scientist. And this was only the tip of the iceberg. I mean, Oki unfortunately passed away in 2010. We took his model and we developed it into a leaky box model that you see here. And after we did our final leptonic model, time evolution model of pulsar with nebula. There is another coloradium about our galaxy that I will not say before being killed. And what we learn, okay, we see that ancient pulsar with nebula are a very natural way to explain unidentified sources. And indeed, with our latest models, we can explain at least 90% of the unidentified sources. If, at least now we take again the hypothesis that the determination shock of the pulsar, we could accelerate hadron as well, this can help a lot in explaining the cosmic ray model. We have seen that the pulsar with nebula lives at least 1,000 times more than the supernovae remnant limb. and the energy is comparable, or at least in the most pessimistic case, we are speaking about the total energy of 10% of it. For conclusion, we don't have conclusion about the cosmic origin of cosmic rays, otherwise we would have this nice chat in Stockholm or some places like this. But many people are working to find either fine-tuning of the standard models or alternative scenario like the one that I was trying to describe in so short time today. So let's thank a lot these people, and thank you for your attention.
Unfortunately, we have no time for questions, but you maybe have some opportunities during this afternoon and during next day to discuss